This battery was almost forgotten, buried in dusty patents, ignored by modern engineers. It didn't explode, it wasn't shiny, it wasn't new, but it also didn't die. Because today, in the shadow of lithium's rise, it's quietly stepping back into the light. The Zinc-Bromine Battery, a chemistry from the 1800s. Not for your phone, not for a Tesla, but for something way more important. It promises safety without fire, simplicity without sacrifice, and endurance without insane cost. But why now? Why is this ancient design finally being taken seriously? Let's get closer, because sometimes the future begins with something we left behind. If you enjoyed the video, support us with a like. It really helps the channel. The lithium paradox. Lithium-ion batteries shaped our modern world. They power our phones, our laptops, our cars. They're small, efficient, and at first glance, unstoppable. But underneath, there's a problem. Extracting lithium is brutal. It takes about 500,000 gallons of water to mine just 1 ton, and that's devastating in places already suffering from a drought. As demand rises, so does the price. In China alone, the cost of battery-grade lithium carbonate surged over 700% in a single year. And that ripple hits everyone: car makers, solar developers, even you and me. Then there's safety. Lithium batteries overheat, they ignite, and when they burn, they don't go quietly. Some fires last for days, others release toxic gases, forcing entire neighborhoods to lock their doors and stay inside. Yeah, they're powerful, but they come with baggage, and recycling them is still messy and dangerous. Yet, lithium dominates, not because it's perfect, far from it, but because alternatives just haven't been good enough. At least until now, because another battery is stepping forward. An old one that never got a fair chance. Zinc-Bromine uncovered. Zinc-Bromine batteries aren't new. The first patent dates back to 1885, but most of the time they were ignored. Too bulky, too niche, too weird. That's changing. At their core, zinc-bromine batteries are a redox flow battery, which means they don't rely on tightly packed solids like lithium. Instead, they use tanks of liquid electrolytes. One tank with zinc ions, the other with bromine. These liquids get pumped through a cell stack separated by a membrane. As they flow, they swap electrons in a redox reaction, creating electricity. And when you charge it, the process just runs backward. It's clever. Want more power? Add more cells. Want more storage? Just use bigger tanks. It scales in a way lithium never could. And here's the kicker. Flow batteries don't catch fire. Their electrolytes are water-based, non-flammable, and stable. You can discharge them down to 0 without degrading them. Zinc-bromine might just be the most promising version. Cheap, abundant materials, safe storage, a perfect match for solar and wind. If only someone could make it practical. Jellyon's solid reinvention. That's always been the issue, making flow batteries practical. Pumps, pipes, and tanks worked, but only at scale. Then came Jellyon, an Australian company that didn't just refine zinc-bromine chemistry, they reimagined it. Their battery, called Endure, ditched the pumps and tanks entirely. Instead of liquids flowing around, Jellion used a gel, a thick, stable electrolyte sandwiched between zinc and bromine plates. From the outside, it looks like an old-school lead-acid battery, but inside, it's something completely new. No lead, no sulfuric acid, just a fire-resistant gel with zinc and bromine quietly doing their job. And because of that design, the Endure battery doesn't need active cooling. It doesn't need complex management systems, and it doesn't need billion-dollar factories to build. Jellyon says 18 of the 22 manufacturing steps can be done in existing lead-acid plants. No gigafactory, no massive investment. Just a smarter use of what we already have. It's compact, rugged, and it's already rolling off production lines. And 137-year-old chemistry reborn without the plumbing. Redflow ZBM3. While Jellion reshaped the form, Redflow stayed true to the flow. Their ZBM3 battery is a classic zinc-bromine redox system. Tanks, pumps, the whole deal. But outdated? Not even close. Redflow leaned into what flow batteries do best: resilience and modularity. Their units are made for harsh, remote environments, places where lithium overheats and fails. Telecom stations in the Australian outback, off-grid homes, industrial microgrids. Each battery stores 10 kilowatt hours and is built for full daily cycling. Drain it to zero, recharge it every single day, no damage, no problem. Try that with lithium, it won't last long. The ZBM3 operates in temps up to 45 degrees Celsius with no cooling. It even cleans itself through something Redflow calls a strip cycle, dissolving unwanted zinc buildup naturally, no technician required. In 2023, Redflow kicked off mass production in Thailand, and later that year, they expanded into North America through a deal with Empower Energies. Their strategy is simple: build batteries where the grid doesn't reach, where diesel is expensive, where safety matters more than size. It's old chemistry, but it works where modern tech can't. And here's where zinc-bromine shines. Because when lithium fails, it fails hard. Thermal runaway, fires, explosions. One bad cell can take down the whole system. We've seen it happen. Tesla megapack fires in Australia and California burning for days, releasing toxic gases. Fire crews couldn't just spray water and walk away. These weren't normal fires. Zinc-bromine avoids all that. Its electrolyte is water-based, non-flammable, and stable, with no risk of thermal runaway. Even under stress, it won't burst into flames. And Jellion pushes it further. Their gel doesn't just resist fire, it can actually suppress it, because bromine, strangely enough, is a natural flame retardant. They even showed a battery still working while sitting on a 700C hot plate. Compare that with vanadium flow batteries. Yeah, they're safe too, but vanadium oxide is highly toxic and dissolved in corrosive sulfuric acid. Handling it and disposing of it is a nightmare. Zinc-bromine isn't perfect, but bromine can still be hazardous if mismanaged, but it's stable and it reeks. If it leaks, you'll smell it instantly. In a world full of risky chemistries, that kind of quiet safety matters. And here's the part nobody expected. Zinc-bromine is cheap. Compared to lithium and vanadium, it beats them across almost every metric. Raw materials: a 2017 study put vanadium flow batteries at about $124 per kilowatt hour in chemical costs, while zinc-bromine was just $8. And system costs? A 2021 analysis found zinc-bromine batteries averaging $153 per kilowatt hour in material costs, while vanadium hit $591. And here's the kicker. They don't need HVAC, they don't need fire suppression, they don't need custom-built enclosures. Jellion made it even smarter. By using the same casing as lead-acid batteries, they avoid building brand-new factories. 82% of Endure's manufacturing steps use the same old machines. Retrofitting a plant for 1 gigawatt year of production costs around $16 million, while building a new lithium-ion plant of the same scale costs $130 million. And the cooling bill? Basically gone. Both Redflow and Jellion say their units run without AC, even in brutal climates. When it comes time to install, shipping, setup, integration, it's all simpler. For long-duration grid storage, those savings add up fast. Real-life performance. And zinc-bromine doesn't just compete, it endures. Redflow's battery lasts 4,500 cycles. Jellion's Endure is rated for 5,000. That's more than twice the lifespan of lithium-nickel systems. Even LFP cells rarely pass 2,000 to 3,000 cycles. Round-trip efficiency? Solid. Jellion reports 85 to 90%, right in line with lithium. And temperature? Lithium can't even touch it. These batteries handle 45 to 53 degrees Celsius with no external cooling. They're already out there, in deserts, remote towers, fire-prone regions. Not lab prototypes, not someday projects. Real deployments, running now, every single day. quietly powering homes, towers, off-grid systems, not because they're trendy, but because they work. Not for every job. Now let's be real, zinc-bromine isn't the universal battery, and that's okay. It's too heavy for EVs, too big for your phone, too slow for some high-drain uses. But where it fits, it excels. Long-duration storage, solar and wind buffering, remote infrastructure, rural electrification. It shrugs heat, abuse, and daily cycling. It stores energy safely for hours or even days. Yeah, dendrites are still a concern, but Redflow's strip cycles and Jellyon's porous membrane both tackle it head-on. Zinc-bromine has limits, but it has a role. Lithium will keep its crown in mobility, but zinc-bromine doesn't want the throne. It just wants the grid. The future of energy won't rest on a single battery. It's going to be a patchwork, each chemistry in its place, each system